Alright, this is a quick little video I'm calling Radicals 1.5 for people who are needing a few more examples to kind of get their minds wrapped around this idea of simplifying radicals. The first thing we need to understand is that square roots make twins singles. So square roots take two things that are the same and make it one. Cube roots make triplets singles. Means it takes three of the exact same thing and makes it into one. And fourth roots make quadruplets singles, so four of the exact same thing turns it into one, and so on. So that means with square roots, the square root of 4 equals 2 because there are two 2's inside of a 4. And so that square root's taking those two 2's and making it a single 2. It's undoing the squaring of those 2's and taking it back to a single 2. Similarly with cube roots, if I have the cube root of 8, that equals a 2. And the reason why is because of inside of an 8 are three 2's. I broke it apart into 2 times 4, and then the 4 breaks into 2 more 2's. That gives me three 2's that are multiplied inside of an 8, and the cube root takes those three 2's and makes it a single 2. Another way to think about those three 2's is as an exponent. So the cube root of 8 is the cube root of 2 to the third, and then the cube root cancels out that triplet of the exponent of 3, making it a 2. In the same way, if we did the fourth root of 16, that equals 2, because of inside of 16 are four 2's. So the fourth root takes those four 2's and makes it a single 2. So that's what's going to be happening. Now we're going to look at ones where it's not all just simplified down to a single number. Alright, let's say we have the square root of 32. First, to see what's inside of that 32 as multiples, we need to do a factor tree. 32 is 4 times 8. The 4 breaks down into 2 times 2. The 8 will break down into 2 times 4, and then I can break that last 4 down into 2 more 2's. You always want to take your factor trees as far as you can until all of the ends of the rows are prime numbers. Now I have all these 2's. I'm doing a square root. A square root takes twins and makes them singles. So I'm going to group up some twins. I can make these two 2's a twin. It doesn't matter how I group these. I can make these two twins. This guy here doesn't have anyone to partner with, so it's kind of left out. So this first group here is going to become a single 2. This group here will become a single 2. And then this 2 we can't square root, so we leave it under a square root because we're not actually going to be square rooting them. These two got rid of their square root because we square rooted them from two 2's to a single 2. Okay? So if I write this over here with the problem, what that would look like is the square root of 32. I'm going to turn one set of 2's into a single. I'm going to turn another set of two twins into another single. Everything's being multiplied, so those will end up getting multiplied together. And then the one that can't be square rooted because it doesn't have a twin to square root it. And then that just multiplies together to be 4 square roots of 2. Another way I can write that, kind of breaking down the steps, is instead of just doing that square rooting from the factor tree over to the problem, I could instead say, put an or here so you don't think I'm progressing, I could say that that first group of 2's is a 2 squared, the second group of 2's is a 2 squared, and then I have that other 2 that's left out, and all this stuff is being multiplied. Then if I square root a 2 squared, I get a 2. If I square root the other 2 squared, I get a 2. And then the 2 that isn't squared has to stay under the square root because we can't square root it. So that's going to be 4 square roots of 2. Same thing, just a different way of showing the work. Now for part B, I want to look at the cube root of 32 to see how that works out differently. Now I'm still working with the same factor tree of 32 because same 32, same guts. The index here tells me what size of sets I'm going to making. A cube root takes 3 things and makes them singles. So now I'm going to group in 3s. So I can take this here, I've got 3 2s, and you can group any 3 of them, it doesn't matter. And then this 2 and this 2 don't quite make a triple, so they're going to get left behind. What that ends up looking like is, over in the problem, the set of 3 2s, it's not working, becomes a single 2 without the radical. And then we have the 2 2s that didn't make it to a triplet. They're going to stay in the radical because we can't cube root them. It stays a cube root. That doesn't change. So then I want to write this over here. This becomes 2 cube roots of 4. All right, I'm going to show this one the other way too in case you like that way of showing it better. So basically my group of 3 2s up there that I put a circle around, those represent 2 to the third. And we're still under the radical. So we have the cube root of 2 to the third. So that's the stuff that's in the circle, and then we still have these other 2 2s. We can write them as 2 squared, or we can write them as 2 times 2. It doesn't matter. So a cube root cancels out a cube. So the 2 to the third will become a 2 when it's cube rooted. But we can't break down the 2 squared because we don't have a triplet, so we'll just multiply that out to a 4. Get the same result, same thought process, just showing the work a different way. All right, now let's look at one that's not all the same number. This all broke down into a bunch of 2s. Let's look at some where it breaks down into some different numbers. All right, let's look at the cube root of 270, and we'll start by making a factor tree for 270. All right, with 270, you can divide it by 2, you can divide it by 3. I see that 10 goes into it because it ends in a 0, so I'm going to start by splitting off that 10. It doesn't matter what you start with as long as you keep going all the way to the end. I gotta take my extra 0 off there. And as long as you go all the way down to primes, all the primes will always be the same. So I'm going to split the 10 into 2 and 5. And then I can split the 27 into 3 and 9. And that 9 will go further into 3 and 3. That gets it broken down all the way into primes. Now I can start grouping things up. My index here is a 3, so I'm making triplets. I can group 3 3s into a set of 3. But I only have a single 2 and I only have a single 5, so they're not going to get grouped up. So that set of 3, the cube root's going to turn into 1 3. And then the other 2 we don't get to actually cube root. So what that looks like is the set of 3 becomes a 3, and then the other 2 we can't cube root, so they're going to stay under the cube root, the 2 and the 5, and everything's being multiplied. So then when I simplify that, I get 3 cube roots of 10. All right, I'll also show this the other way in case you're liking that way of looking at it. So with that, we would say that we keep everything under the radical. We're taking the cube root of everything that multiplies up to 270. So that's 3 to the third times a 2 times a 5. Now I can actually cube root 3 to the third because the cube and the cube root cancel each other out. So that's going to make a 3. But the other stuff I can't cube root because I don't have triplets to do it. So they are going to stay under the radical. And then we need to multiply them together as for the final simplification. So you get the same thing, Just different way to look at it, different way to show it on paper. I like to think about these, it's kind of like playing cards, where sometimes you can lay down pairs, sometimes you have to have 3 of a kind to lay down, sometimes you have to have 4 of a kind to lay down. So your index is telling you what size of sets you can lay down. So here we have a cube root, so we can lay down 3 of a kind. Can't lay down more or less. And so it's like the ones that end up outside the radical are like your 3 of a kind that you lay down on the table. And the other ones are what you have to keep in your hand because you don't have enough to lay anything down on them. So that's kind of just a metaphor to help you with it. It doesn't explain the math, but kind of helps you keep straight of we're laying stuff down on the table. But in those games where you're laying down 3 of a kind, 2 of a kind, it doesn't really matter what the set is. You just get counted as sets. So it turns that 3 of a kind into 1 set. So if that's helpful, that's a way you can think about it. Let's do one more example then. All right, let's look at the square root of 180. So first I'll break it into a factor tree with 180. So that gives us 10 and 18. Then I can break the 10 into 2 and 5. And then I can break the 18 into 9 and 2. And then I can break the 9 down into 3 and 3. And then that gives me everything's broken down as far as it can go. In this case, I'm doing a square root. So my index is a 2. If there's not an index written there, it's an index of 2, and it means it's a square root. So now I'm making sets of 2's. Identical twins. So I can make a set of 2 3's. And then there's a 2 here, and all the way over here on the other side is another 2. This is making it look like a clown face. And then there's this 5 that doesn't have a partner. So that's going to not be square rooted. So what we get is the set of 2 2's is going to become a single. The set of 2 3's becomes a single. And then the 5 can't be square rooted, so we just leave it as the square root of 5. It's like a symbolic representation of it. And then this becomes 6 square roots of 5. Written the other way that I've been writing it, this would look like the square root of 2 squared times 3 squared times 5. Now, since I have an index of 2, my index of 2 is going to cancel out the squares. That's how squaring and square roots cancel each other out. So we have the 2 times the 3, but then the 5 is still being square rooted. So hopefully this helps give it a little bit more clarity. Got to finish it up there by going ahead and multiplying together the 2 and the 3. So that gives us the same thing we had before, just showing the work a little differently. Give that a try, see if that works out for you.